Imagine holding a single invisible particle in the palm of your hand. It has no charge. It barely interacts with anything. It's smaller than an atom, lighter than a whisper, and completely silent. Now imagine that this one particle, under the right conditions, could level a city, vaporize steel, and reshape the course of human history. This isn't science fiction. This isn't exaggeration. This is the strange, terrifying, and beautiful truth about the neutron. And to understand how something so small can do something so catastrophic, we need to take a journey into the heart of the atom, into a chain of events so improbable that even the physicists who discovered it didn't believe it at first. Let's start with a question that sounds almost childish. What is an explosion? When you light a stick of dynamite or burn a tank of gasoline, what's actually happening? The answer is that you're rearranging the bonds between atoms. Electrons shuffle around, molecules break apart, and a small amount of stored energy is released as heat and light. Chemistry, in other words. Powerful, yes, but limited. Even the most violent chemical reactions only release the energy stored in the outer shells of atoms, the thin electron clouds that govern how molecules dance with each other. The nucleus, the dense little kernel at the center of every atom, just sits there, untouched, holding on to a secret that for most of human history we didn't even know existed. That secret is binding energy. Inside every atomic nucleus, protons and neutrons are glued together by what physicists call the strong nuclear force, the most powerful force in the known universe. It's so strong that it overcomes the natural electrical repulsion between protons, which by all rights should fly apart from each other instantly. Pound for pound, the energy locked inside a nucleus is millions of times greater than the energy locked in chemical bonds. If you could find a way to break that nuclear glue, even just a little, you'd unleash something the universe usually keeps hidden behind a vault door. And in 1938, in a laboratory in Berlin, two chemists accidentally cracked that vault open. Their names were Otto Hahn and Fritz Strassmann, and they were doing something that on paper seemed boring. They were bombarding uranium atoms with neutrons, hoping to create heavier elements. Instead, they found something impossible. After the bombardment, their uranium sample contained barium, an element roughly half the size of uranium. It was as if they'd thrown a marble at a bowling ball, and the bowling ball had split into two smaller balls. Hahn was so confused that he wrote to his former colleague, the physicist Lise Meitner, who was hiding in Sweden after fleeing Nazi Germany. Meitner, walking through the snowy woods with her nephew Otto Frisch, did the math on the back of an envelope, and what she realized changed the world. The uranium nucleus, when struck by a neutron, was splitting. Not chipping, not decaying, but splitting nearly in half. And when Meitner calculated the masses involved, she found something staggering. The two new pieces, added together, weighed slightly less than the original uranium atom. That missing mass hadn't disappeared, it had transformed. According to Einstein's famous equation, E equals mc squared, even a tiny amount of mass contains an enormous amount of energy, because the speed of light squared is an unimaginably large number. Meitner realized that a single uranium atom splitting could release around 200 million electron volts of energy. That's about 50 million times more energy than the burning of a single molecule of TNT, from one atom, from one neutron's gentle tap. But here's where the story gets truly terrifying and truly elegant. When that uranium atom split, it didn't just release energy. It also released 2 or 3 more neutrons. And those neutrons, born from the wreckage, went flying off at enormous speeds. If there were other uranium atoms nearby, those neutrons could strike them, splitting those atoms too, which would release more energy and more neutrons, which would split more atoms, and so on. This is what's called a chain reaction. And in the right conditions, it doesn't unfold gradually. It unfolds exponentially, doubling and doubling and doubling in a fraction of a second. Let's pause here and think about what exponential really means, because our brains are terrible at it. Suppose you start with 1 neutron. It splits 1 atom and produces 2 neutrons. Those 2 neutrons split 2 atoms and produce 4 neutrons, then 8, then 16, then 32. Sounds slow, right? But this doubling happens roughly every 10 nanoseconds inside a properly assembled lump of uranium. After just 80 generations, which takes less than a millionth of a second, you've gone from 1 neutron to over a septillion neutrons. That's a 1 followed by 24 zeros. Each one of those events releases that 200 million electron-volt punch. Multiply that by a septillion, and you have the energy of tens of thousands of tons of TNT, all unleashed in a flash shorter than a heartbeat. That, in essence, is an atomic bomb. Now you might be thinking, if it's that easy, why isn't every chunk of uranium ore on Earth a ticking time bomb? Why don't natural deposits just spontaneously detonate? The answer reveals one of nature's quiet kindnesses. Most uranium in the world is uranium-238, which is stubborn. It doesn't fission easily. The rare cousin, uranium-235, makes up only about 0.7% of natural uranium, and is the only one that fissions readily when struck by a slow neutron. To build a bomb or a reactor, you have to enrich the uranium, painstakingly separating the two isotopes, which differ in mass by only 3 neutrons. It's one of the hardest industrial processes on Earth. Nature, in her wisdom, made the doomsday element exceedingly rare and exceedingly difficult to extract. But there's another safeguard, and it's geometric. For a chain reaction to run away with itself, you need what's called critical mass. If your lump of uranium-235 is too small, the neutrons born inside it tend to escape through the surface before they can find another atom to split. The reaction fizzles. But if the lump is large enough, the neutrons stay trapped long enough to multiply. The critical mass for uranium-235 is about 50 kilograms, roughly the size of a small bowling ball. Below that, nothing dramatic happens. Above it, the universe shows you what it's been hiding. The first humans to see this happen were the scientists of the Manhattan Project, on a desert morning in July 1945, at a test site they called Trinity. When the bomb detonated, the desert sand turned to glass. The flash was visible from 200 miles away. Robert Oppenheimer, the physicist who led the project, later said a line from the Bhagavad Gita came to his mind. Now I am become death, the destroyer of worlds. What he had witnessed was the unleashing of a force that, until that moment, had only existed inside stars. He had brought a piece of stellar physics down to Earth, and that's worth pausing on. Because the same process that powered that bomb, the splitting of heavy nuclei, is also the cousin of the process that powers the sun. The sun fuses light nuclei together, while bombs split heavy ones, but the underlying principle, the conversion of mass into energy, is the same. Every time you feel sunlight on your skin, you are feeling the residue of a nuclear reaction that started in the sun's core 8 minutes ago. The atom is not just the building block of matter, it's a furnace, and whether it warms us or destroys us depends entirely on how we coax it open. There's a beautiful and unsettling thought experiment that helps make this concrete. Imagine you could shrink down to the size of a neutron and stand on the surface of a uranium nucleus. From your perspective, the nucleus would feel like a quivering, unstable droplet, barely holding itself together. The protons inside are constantly trying to push each other apart with electrical repulsion. The strong nuclear force is barely winning. It's like a water balloon stretched to the breaking point. Now you, a tiny neutron, drift in and gently touch the surface. That tiny perturbation is enough. The droplet wobbles, elongates, pinches in the middle, and snaps in two. The protons, no longer held back, recoil from each other with explosive force. You didn't push, you didn't slam, you barely whispered. But the nucleus was already on the edge, and your whisper was all it took. This is why we say a single neutron can destroy a city, not because that one neutron carries the energy, but because it triggers a cascade. It's the first domino in a chain that already wanted to fall. The energy was always there, locked inside billions of nuclei, waiting. The neutron just opens the gate. This same principle, controlled instead of unleashed, is what powers nuclear reactors. In a reactor, engineers slow down the chain reaction with materials that absorb neutrons, like control rods made of boron or cadmium. They keep the multiplication factor at exactly 1, meaning each fission produces, on average, just one more fission, steady, sustainable, predictable. The same physics that destroyed Hiroshima also lights up entire cities through nuclear power plants, providing about 10% of the world's electricity. The difference between catastrophe and clean energy is, quite literally, a few neutrons in either direction. And here's a counterintuitive twist that most people never hear. In many nuclear reactors, The neutrons released by fission are moving too fast to be efficiently captured by uranium-235, so engineers slow them down with a moderator, usually water or graphite. Slower neutrons are more likely to be absorbed, which helps the reactor maintain a steady chain reaction. But a bomb is different. A bomb does not wait for calm, moderated neutrons. It depends on a violently fast chain reaction, packed into a supercritical mass before the material can blow itself apart. Same particle, same nuclear doorway, completely different tempo. Even more strangely, neutrons themselves are unstable when they're alone. A free neutron, drifting through empty space, will decay into a proton, an electron, and a neutrino in about 15 minutes. So the very particle that triggers the most violent reactions humans have ever engineered is itself a fleeting, transient thing, a ghost with a deadline. It's only when bound inside a nucleus that neutrons become stable, and only when freed by fission that they can wreak their havoc. There's something almost poetic about that. The destroyer of cities is, on its own, a dying particle. So the next time you hear about nuclear weapons or nuclear power, remember this. The story isn't really about uranium or plutonium or bombs or reactors. It's about a single, neutral, quiet particle and the staggering amount of energy that the universe has been hiding inside every atom since the beginning of time. We didn't invent that energy. We just learned how to ask for it. And the question that should haunt us and inspire us is this. If a single neutron can release the energy of a star, what other secrets is matter still keeping from us? What other vaults are out there, waiting for someone to find the key? Because if the 20th century taught us anything, it's that the smallest things in the universe often hide the biggest answers, and we've only just begun to listen.